So we're on part 2, understanding and troubleshooting memory problems. And the reason I think this is an interesting section is that memory-related issues can be behind serious performance problems. Process memory leaks, we're going to see, may cause system failures or other process failures. Just like a process that is opening handles can cause the system to stop working, basically. A process with a memory leak may also cause the system, in effect, to stop working because no more processes can be created. Other apps may not be able to allocate private memory. So we're going to look at how to deal with memory leaks, both in a process as well as at the OS level. And that's even more serious. A bug in a driver or a piece of Windows that is not freeing system memory. We'll talk a little bit about how to answer this question. And that's an interesting one. How do you prove that you need more memory? And you might be disappointed by the answer. It's really difficult to absolutely prove, and there's no single performance counter that tells you for sure. If I ask you that now, what performance counter would you look at to determine if you need more memory? What would you say? Anybody? Page fault activity. And if you've looked at Windows, you might be aware that there's 2 different counters for page faults. There's soft and hard page faults. So if you looked at soft page faults, you'd have the wrong answer. Soft page faults are page faults that are handled by referencing something that's in memory already. So adding memory is not going to help if you have a high soft page fault rate. Hard page faults is also potentially misleading because if you run a different exe every second, if I run Solitaire, Notepad, Outlook, Minesweeper, PowerPoint, Excel, Firefox, what's my hard page fault activity going to show? Will adding memory make starting an app the first time faster? No. So hard page fault activity by itself may be misleading. On top of that, how does PowerPoint read the PPT file off the disk from our previous discussion? Page faults. So if I open PowerPoint, I start PowerPoint, and I open a PPT file and page down to the end. Open another PPT file, page down to the end. Open another PPT file and page down to the end. Same with Microsoft Word. I open a Word doc, and I open a different Word doc every second. What are you going to see in terms of page reads? Heavy page read activity. Will adding more memory help or improve performance of opening a different document every second? Obviously not. So basically, page reads by themselves tell you nothing. They don't prove that more memory is going to help. So how can you do it? We'll see later in the presentation. We'll talk about sizing the page file, and we'll talk about the meaning of the core memory counters. I have a couple of introductory slides, just like we gave a definition of processes and threads. Just a couple of things about the Windows Memory Manager to set the stage. Windows implements a demand-paged virtual memory approach, meaning that stuff comes in on demand. When you run Solitaire, how much of solid.exe comes off the disk when you run it? Only a little bit. Only the part that was referenced to actually draw the initial window. As you start to use Solitaire, you might call upon other features of the app where the code is still on the disk, and that triggers a page fault. Likewise, when a DLL is loaded, how much of the DLL comes off the disk? Only a little bit. And it comes off on demand. In fact, that's why I dislike the term loading a DLL, because to say loading a DLL implies what? It implies that the DLL is being read off the disk in its entirety. That's not true. Only the part that is referenced is read. Now, as of XP and later, and I'll talk about this a little more later in the presentation, there's a new demand that is put upon app startup, and that's called the logical prefetcher. Whenever you start an exe on XP or later, the system looks for a file in the Windows directory that has a record of the parts of the exe and the DLLs that were referenced the last time you ran the app during its startup, where its startup is defined as the first 10 seconds. So again, on XP and later, every time you create a process, the system makes a record of the page fault activity that occurred during the first 10 seconds, records that in a file, uses that the next time to preload or prefetch to improve app startup. So it's still demand virtual memory. It's just that process startup, the system is demanding more It's demanding all the stuff that was referenced the last time you ran it during the first 10 seconds. And that actually, you might think it slows things down. It helps because these I/O operations are collected together and done in big reads rather than read here, read here, read here, go back and read here, which causes a lot of what on the disk? Seeking. The other part of the prefetch mechanism is that behind your back every 3 days, the system defragments the files involved in each app startup group. So that means that when you run Solitaire or Outlook the next time, if it's been 3 days, the files that it touches have been physically defragmented to be contiguous on the volume. So now not only is it collecting all the reads together in big reads rather than lots of small reads, it does the reads contiguously on the disk, which again reduces disk seek time. So that's something that just is happening behind your back. I don't know if you've noticed that app startup is a little bit better on XP, but that's one of the things they did to improve app startup. When are pages written to the disk? So when does something get paged out? Only when necessary. Only when nobody has used that data for so long that the system needs to use that memory for something else. The other thing about outpaging is that what gets paged out? Only stuff that's not already on the disk. So if you run Solitaire, in-paging occurs. Does the system have to save the pieces of sol.exe that it read from the disk in the paging file? No, because where is it? It's on the disk in sol.exe if it needs it again. Unmodified code is paged in. It's never paged out. Make sense? Why page out something that's already on the disk? DLL code that's paged in is not paged out because it can reread it later. So what gets paged out? Private process modified data. An example would be in this notepad window, the text I am typing now is private process memory that could be paged out. The buffer that contains that text could get paged out. The code, the part of notepad.exe that's in RAM right now, doesn't get paged out. Now, the memory that contains this text, when is that going to get paged out? If I switched away from PowerPoint, but left the process there, and never switched back to that, ultimately the memory manager is going to visit that process and slowly take its physical memory size down. A process whose threads are asleep becomes a candidate to put on a diet. And the memory manager performs, you know what liposuction is? Basically, the memory manager performs liposuction on processes that are either overweight or inactive. And it does that in the context of a system thread called the working set manager. Every second, the system checks whether there are processes that need to have a little bit of liposuction applied. It takes a vacuum hose, basically, and sucks pages out of their process working set, which is their physical memory utilization. And it only does that to processes who the memory manager determines are taking up more memory than they need. And that, again, is a function of either the threads aren't running anymore. That's an indication that there's really not a need to keep that process memory around. Or the process is considered overweight. And there is a way for a process to tell the system its normal body weight. It's called the working set maximum. So if the process memory usage is well over its normal working set maximum, the OS considers it to be overweight, and it puts it on a diet by performing liposuction with a vacuum hose. It sucks pages out. So again, if I never went back to that notepad window again, ultimately the memory usage would get whittled down literally to zero. So that's another myth. Some people say, my system is slow, let me close a few processes. Notepad's thread was in the wait state. Notepad was a well-behaved application that doesn't have a thread that wakes up to do useless work. It only runs when it gets window messages. So is closing Notepad going to improve system performance? Not at all. You might say, well, the memory will be released. And I would say, but the memory is going to be taken away anyway, over time. If the system needs it, it would take that process memory usage and reduce it literally to zero. Now, it turns out there's a little bit of memory that a process uses up that can't be paged out. the data structure that describes the process in kernel memory and the data structures that describe the threads, they can't get paged out. But that's a very small amount of memory. 800 bytes for a process and 600 bytes for a thread. Some small number that doesn't really matter. But the memory space of the process, the address space of the process, that can actually be reduced to 0. That's just a chart for your reference that shows the physical memory usage maximums on Windows, on the various flavors, both 32-bit and 64-bit. It's interesting that the AMD 64, EM64T, the Intel clone of the AMD 64, on running 32-bit Windows on an AMD 64 box can actually address more physical memory than on an x86 on a high-end Xeon server. And that's because the processor has more bits in the page table structures that describe the mapping of virtual to physical. And so there is a memory increase for this 32-bit Windows on an x64 box. Now, by the way, when I say x64, that's the politically correct way to refer to these two implementations, AMD 64 and Intel's clone. Not the Itanium, Intel's clone of the AMD 64 architecture. By the way, they didn't do an exact clone. It's 99%. There's some instructions they didn't implement. So, how do we get an idea of the memory usage of a process? Well, first, let's talk about the sizes of a process memory space. We didn't talk about that in the process section. This morning I said a process is a private memory space. We didn't say how big it is. On 32-bit Windows, by default, each process is given the illusion that it has a private 2 gigabytes of virtual memory. So here's 3 processes that have the illusion that they would have 2 gigabytes of virtual memory, even if the system has 128 megs of RAM. And where does the process memory go that can't be represented by physical memory? Well, page file would be not a completely correct answer, because part of the process address space is the exe, the code. That doesn't go to the paging file. So here's a way to think about that. If I have a process that is a 512 megabyte .exe, a lot of code. It's a really big program. It's the next version of Microsoft Office. It's going to come with its own hard drive. And let's say this particular app allocates very little private process memory. So it's performing massive computation on a single number. How much memory would you need to run this app? You could have 64 megs of RAM. How big a page file would you need to run that app? No page file. Because if you had a 64 meg desktop system and you ran a 500 megabyte exe that didn't create much private data, what happens? The exe is paged off the disk on demand. And as you run through this app, it's reading more and more, and it's overwriting older pieces of the exe that were cached in memory. There's no paging going on. There's no outpaging because, again, the only thing that goes to the paging file is private modified data. So it really depends on the app's behavior and how much private memory it creates. So that's why I said you could run, for example, 3 or 4 or 10 2 gigabyte processes on a system with 128 megs of RAM and no paging file, and it might work if those processes were consisted of mostly read-only code, because the code will get paged in on demand and the memory overwritten without having to save anything to disk. So each process has the illusion of a 2 gigabyte address space. Now, it's interesting that the reason why Microsoft divided the 32-bit address space in half, because the other half is dedicated to the OS. So just like each process has the illusion of having 2 gigabytes, the OS and the drivers also live in a 2 gigabyte sandbox, and they don't always live happily together. And when they don't live happily together, we get screens of this color. The reason that it was divided in 2 and 2 was because of one of the early CPU architectures that Windows ran on, the MIPS R4000. NT 3.1, 3.5, 3.51, and 4.0 were supported on the MIPS architecture. That processor architecture forced the OS to divide the address space in half. It didn't support per process virtual mappings at the 2 gig boundary. When Microsoft dropped support for the MIPS, then they said, wait a minute, we don't have to limit a process to 2 gigabytes. Let's give an option to have a bigger address space. And in NT4 Service Pack 3, an extension of the memory manager was added that allowed you to configure the system for a process to be up to 3 gigabytes instead of 2. And that was the 3GB switch in boot.ini. That was added in NT4 Service Pack 3. That 3GB switch now is supported on the client as of XP Service Pack 2. Prior to XP Service Pack 2, this only worked on big servers. Windows 2000 Advanced Server, NT4 Enterprise Edition server, and Windows Server 2003 Enterprise Edition and up. Now it works on client machines. Because if you think about it, it's perfectly reasonable that a desktop app might need more than 2 gigabytes of virtual memory. Can you think of an example desktop app that could use more than 2 gigabytes of virtual memory? AutoCAD with a very complicated CAD diagram. Photoshop with a very complicated graphic with lots of layers. Video rendering. So it's perfectly reasonable that 32-bit apps on the desktop, not just the server. Because the obvious case, and the reason they put this in originally, was for server applications like SQL Server, which want to be able to manipulate more database data. So 3GB now works for the client, not just for servers. And they also added in Server 2003 an option where you can choose between 2 and 3 /user VA. So that's between 2 and 3. Now, why is it not 3.5 or 3.8? Because notice who gets smaller? The OS sandbox or memory space. So 32 bits is 4 gigabytes. You got to draw the line somewhere. And because Windows maps the OS and the drivers in the address space of each process, there has to be some minimal size. And so they picked 1 gig of virtual memory. Again, this is virtual, not physical. So would it work if the OS address space was half a gig? Maybe on some systems. Now, it turns out that Linux actually has an interesting option where you can have a 4 gigabyte process space and a 4 gigabyte space for the OS. It's a kernel patch. It's not in the mainline Linux. And the way they do this trick is when a thread makes a system call, they do a context switch to another process, which is the OS, that now has full 4 gigabytes. Serious performance penalty for that, because context switching is relatively expensive compared to a subroutine call. So on the normal Linux kernels and on Windows, when a thread makes a system call, it is in effect calling a subroutine in a DLL. The operating system is the DLL. There's no context switch when you make a system call, because the OS code and the driver code is mapped into the address space of each process. And that's the way most OSs work. But interesting that there is a way, even on the x86, to give processes 4 gigabytes and give the OS 4 gigabytes, but it requires then context switching when moving from process to OS and back. And that's expensive. Now, by the way, if you boot 3GB, for example, if I rebooted my laptop, which is running XP Service Pack 2 3GB, and I typed and typed and typed and typed, how big, virtually, would this notepad process grow to if booted 3GB? Answer A, 2. Answer B, 3. Let's take a vote. Who says A? Who says B? A was right. And that's because, it's on the slide, the image has to be specially marked as I'm a large address space aware exe. There's a bit in the image header. So if you boot 3GB and create a process, unless that bit is set, the process is limited to 2. That's to avoid potential application bugs because the programmer assumed a 2 gigabyte address space. And that was the promise. The picture looked like this from the start. The documentation for the Windows NTOS said processes will never be bigger than 2. And so when they broke that rule, they took the conservative approach of a process has to be specially marked. Now, how do you mark the process? There's a reference to the same tool that I talked about this morning. Do you see it? Image CFG. Now, is it safe to set that flag on a random exe? Probably it's going to work. But it's a flag really the programmer should be setting, because they need to make sure that their app is not going to break. Turns out that flag is on several images in the Windows directory, And you can query this list yourself using ImageCFG. So if I use ImageCFG to look at every exe in the Windows System 32 folder, pipe the output to a text file. So this is opening every exe and giving a little output of its image stats. Now it's getting some errors for exes that are in use because it can't do what? Open the file exclusively because it's in use in some other address space. And if you look at the text file that results and search for the word large, you'll find out that there are several system images that have this large address space aware bit set. One example is lsass.exe. LSASS is the security server process in which Active Directory runs. So on a domain controller that is booted 3GB, the LSASS process will, on a very large Active Directory database, take advantage of the larger process address space, and you'll get better performance. What's another Microsoft server application that can be configured to use more than 2 gigs of private address space? Exchange, SQL Server. So there are definitely cases where this helps, but it's interesting that several exes in the OS are configured with that large address space aware bit. Now on 64-bit Windows, the memory space is a little bigger. Instead of 2 gigabytes by default, it's 8,000 gigabytes per process. Now Microsoft picked this number because the Microsoft Office team thinks that that will be big enough to support the 64-bit version of Outlook. They're not sure. It's very close right now. They're just at the boundary. But it looks like 64-bit Outlook will fit in 8,000 gigabytes. I'm joking. There are actually some low-level technical reasons why this number was picked. This number is clearly not half the 64-bit address space. 64 bits is 17 billion gigabytes. 32 bits is 4 gigabytes. So half of 17 billion is not 8,000. The takeaway point here is that there's lots of breathing room. The OS memory, if you add it together in the current version of 64-bit Windows, has a max of about 6,000 gigabytes. That picture isn't really showing how things are laid out. It's not one contiguous region. There are separate regions for the different components of OS memory, loaded drivers, kernel memory, system page tables. If this picture was drawn to scale, the system memory box would be somewhere in the parking lot across the street because there's a massive gap from the end of the process address space to the start of system address space. So the point is there is lots of expansion room possible in the 64-bit system today. These are implementation numbers that were picked for the first version of 64-bit Windows. Now, by the way, you know that the 64-bit platforms that Windows runs on today aren't really giving 64-bit virtual addressing. These are hardware limitations in the current processor architectures that Windows runs on that provide 64 bits. The x64 platform, in fact, only gives 48 bits of virtual address space. So 262,000 gigabytes is possible. Again, only about 16,000, 17,000 gigs have been defined now. So there's still a lot of expansion potential with the current 64-bit chips. So if you look at the process address space, what stops me from creating more and more and more and more processes? So if I kept making new processes over and over and over again, what would ultimately cause me to run out? What would run out? Well, somebody said physical RAM. This is a virtual memory OS. Can it page stuff out? Well, there's a couple of resources that would ultimately limit the number of processes. And the one that we're going to focus on here is the system commit limit. I'll bring up Task Manager. And that's the number on the lower left in the commit charge section, the system commit limit. That's the total amount of private virtual memory that the system can keep track of on your box. Notice I said private, non-shareable virtual memory. So again, my illustration of Notepad. When I start typing in Notepad, the private memory that contains the text, that's what I mean by non-shareable private memory. because notepad.exe, the code, is shared. So if I ran an app that didn't create much private memory, how many times could I run it? Thousands of times. Each process has a small amount of private virtual memory, and that's because every thread in a process has some private storage called the thread stack. So I would ultimately run out of system virtual memory even if I kept running an exe that didn't have much private memory, because every process, even if it does nothing, has a small amount of private memory. The system commit limit, therefore, is a function of what two resources? It's the sum of your page files and RAM. So if your system commit limit is too low, you can either increase the size of your page file or add RAM. Either one makes the commit limit go up, because the system keeps track of private committed memory either by keeping it in RAM or storing it in the paging file. Now, the reason that says most of RAM is that given a system with this much memory, when you boot, some of the memory is taken by who? The OS. The OS has some non-pageable driver and OS code and data that can't be saved to disk. So what's an interesting number to look at is on your system sometime, take your commit limit, subtract the size of your page file, and what number will you be left with? That most of RAM number. That's a way for you to find out how much memory was stolen from you by the OS. Shall we do it on my box? Okay, so how can I check my page file size? My computer properties, advanced, performance settings, really advanced, change. This is yet a fourth button. Now, if you get here, you're really smart. So my page file is a fixed size of 1,000 megabytes. So I want to take the 1,000 megabyte page file that I have and subtract it from my commit limit. Now, the commit limit is expressed in kilobytes, so I need to convert one unit to the other. So I'll bring up calc, and let's take my 1,000 megabytes, 1,000. How do I convert that into kilobytes? Times 1024. All right, so I have 1,024,000 kilobytes of page file. I'm going to subtract that from the commit limit, which is 1971824 minus 1971824, and I'm left with 947,000 kilobytes. Now, how much physical memory is on my machine? You see the physical memory total there? I have a gig laptop. Again, this is in kilobytes. So look at the difference. Let's add that and get the exact difference. So I'm going to say plus 1047920. 100,000 kilobytes. Let's convert it into megabytes, dividing by 1024. 97.7 megabytes of my gig has been stolen from me. It's being used by the OS. It's not for me directly. So that's interesting. About 10% of my RAM isn't available for process memory utilization in file cache. Now, I'm not saying that's bad, and it's not always 10%. It could be between 5 and 10%. If you look on a smaller memory machine, it's closer to 5 or 6%. It's not computed, by the way, in terms of a percentage. It is a function of the drivers that you're loading and how system memory pools are configured. But it is interesting that of the RAM on your box, it's not all for you. It's not all available for process memory utilization and file cache. But that's a quick way, again, subtract the page file size from the system commit limit. Now, let's talk about process memory utilization. When a process is born, when I run sol, that process starts out using 0 memory. And as it starts to fault in pages, its working set grows. And again, prior to XP, that page faulting occurred literally piecemeal. As the thread began running, a page fault occurred. It ran a little more code, a page fault occurred, and so on. The working set was assembled dynamically. In XP and later, there's a little bit of an optimization to prefetch the pages to speed up the app startup. Nonetheless, the working set always starts as 0, and due to page faults grows. So the working set is essentially the physical pages owned by a process. Here's the way I like to look at the working set. Of the virtual address space of a process, the working set are the parts of the process virtual memory that if a thread touched that address, it would not get a page fault. Think of it that way. It's the part of the process virtual address space, which could be this big, that if a thread in that process touched that address, it would not get a page fault because it's in the working set. Now, by the way, if it touches part of its memory space that's not in the working set, that doesn't mean it's going to go to the disk if that piece of the process address space is where? In RAM, because it was cached. Simple example of that is I run solitaire again. I'm now running 2 copies. The second solitaire went through the same set of page faults as the first one. But those didn't go to the disk. Those were resolved how? Sharing the page. Windows automatically shares any shareable piece of memory. There is no way to turn that off. In other words, there's no way for me to run solitaire a third time and tell the system, don't use the copy of sol.exe or the pieces of sol.exe that are in RAM. I want you to reread it from disk. There's no way to tell the system to do that. If there's a piece of a memory map file in RAM, it will be reused. You can't turn that off, which is a good thing. Because, by the way, that means when you add memory and you don't increase the workload of the system in terms of the number of processes, how will the system use the extra memory? File cache. It just works that way. Now, of course, if I copied sol.exe to another folder and ran it, it's going to have to reread it from disk because that's not the same sol.exe that I'm running right now from the Windows directory. Likewise, if I go and bring up a piece of this process, like the help about, that might have just got a page fault. I don't know. I've never done the help about, let's pretend, since I booted the system. So the working set of this process is maybe a little bigger than the other guy. If I go and do a help about, that was no disk I/O, I'm sure. Because if he is referencing a piece of the code that another process had already brought in from the disk, they automatically share that copy of the code. Let's map the working set to what's displayed in Task Manager. And I'm doing this because Task Manager is what most people use to look at system activity. And Task Manager, by default, when you start it, is configured to look like this. The mem usage column, which is what most people look at to determine memory usage, is absolutely the wrong column, the wrong number to look at if you're trying to understand virtual memory usage by a process. If you're trying to understand who has a memory leak, because that's the working set size. And that's what's on the slide. Column 1, the mem usage column, is the working set size. And you know what? The app has no control over that, effectively. It's up to the memory manager. The memory manager decides when a process physical memory can grow. And like I said before, when the threads in a process go idle, what does the memory manager do to the working set? Trims it down. So the app has no control of the working set size. The memory manager does. It's an interesting number to look at, but it's not really the right indicator of a memory leak. A process with a memory leak will have a working set that goes to a point, and then what does the memory manager do to that process? It says, stop. You're as fat as you're going to be, physically. Virtually, if you want to keep increasing your size, fine. But physically, you're going to be in this box. So the process continues to create new pages, but as it's creating new pages, the OS is doing what? Taking away. Process wants to create a new page, the OS takes a page away. And it keeps the working set size to some fixed number. So that is not the right number to look at to diagnose a process virtual memory leak. The second column is. That column is not there by default. That's the virtual memory size column. So I'm going to add that now. Again, that's the virtual memory size column. And that column shows the total amount of private virtual memory in the process. That's the unshareable part of the process address space. The part that could be paged out. I like to call that column the PPF, potential page file usage. It's what could be paged out if that process needed to be squeezed out of memory now. So it's not the exe, it's not the DLL code, it's the unshareable private part of the process. It's the part that nobody else can share. So that's the number that goes up when a process has a memory leak. The mem usage will go up to a point. It's the VM size that goes up and up and up and up until it reaches what size? What's the maximum total virtual memory size for a process? On 32-bit Windows, by default, 2 gigabytes. What Process Explorer and perfmon call those two columns is, to me, a little more rational, a little more clear. The base performance counter that Task Manager calls VM size is really called the private bytes. Isn't that a better name for it? Private. It's the private memory for the process. And what Task Manager calls mem usage is called the working set. That's the performance counter if you run perfmon or you add the column in Process Explorer. So I wanted to make the mapping because Task Manager is probably what most of us use for a quick check, and the names of the columns to me are not quite as clear as they should be. So that's the mapping to the perf counter. So when a process reaches its working set maximum, and again, who decides that? The memory manager. A process has reached its physical maximum, but it still wants more. The memory manager takes away. Now, which pages does it take away from a process? It takes away the oldest pages, or the ones that have been accessed longest ago. Windows implements a least recently accessed algorithm to take pages away. That makes sense, right? If you have referenced some stuff and you stopped referencing that and the system needs to put you on a diet, take away the pages that you haven't touched for the longest amount of time. And it's as of Windows 2000 that it does this smarter algorithm. Likewise, when a process is trimmed, so if there's heavy demand for physical memory, Windows will go and perform liposuction on process working sets. So if a new process comes to life, is paging like crazy, he wants memory and he deserves memory because it's a function of the page fault rate that the memory manager uses to determine when the process working set can grow. If you stop paging, then that's an indicator that you don't need memory anymore. In fact, maybe you use too much memory. And so that's when the memory manager might put you on a diet. So the memory manager visits processes and takes pages away when it needs to create free memory. So in either case, the question is, where do the pages go that get taken away from a process working set? It would be stupid to erase that memory. Why? Because if it was in a working set, somebody was using it, which means they might what? Use it again later. So it keeps it in memory for a while, so that if a process references that page, it can come flying back into the working set without going to disk. That's called a soft page fault. No disk I/O. A little bit of CPU overhead, not much. So pages that are taken away from a process are held in memory for a while. If nobody ever touches that page, ultimately what's going to happen? It's going to be overwritten and used for some other purpose. Later, if the process goes to reference that page, what's going to happen? If it references a page that was taken away, that is no longer in memory, it has to reread it from the disk. That's what virtual memory is all about. And then you get a hard page fault. So we're going to look at the paging lists. In other words, how does Windows keep track of these things? And to me, the cool thing that comes out of that is we're going to give an exact definition of what available memory is. And I think you'll be surprised, after looking at the paging list now, to be able to dissect available memory. So we've got a couple topics left in the memory troubleshooting. What happens to the memory taken away from a process? And that takes us into the topic of how does Windows organize physical memory or keep track of the unassigned or unowned physical pages. Unowned means memory not owned by a process or by the OS. There are several lists that the system maintains that keep track of the state of every piece of memory. Now, I'm going to talk about memory moving from one list to another list. Nothing is moving. Pointers are changing. So when I say a page moves from the free list to the zero list, that physical page of RAM is not moving. A pointer is changing. Now, the next two slides have some text that I'm going to talk through with a picture. So I'm going to talk through the text on the 2 slides that I just skipped over, but you have some notes at least. Let's look at the movement of memory and how the system keeps track of free memory. Let's start when the system boots. You power on the system. The memory manager zeroes all the physical memory. This is not the BIOS power on self-test that you'll see checking the memory. This is the Windows Memory Manager at boot time. Goes in and actually zeroes every physical page. So memory is filled with zeros at system boot time. So initially, all the memory is on a list of pages called the zero-page list. And by the way, it was on an earlier slide, but I didn't mention it. The size of a page on an x86 and an x64 is 4 kilobytes, and on an Itanium, it's 8 kilobytes. So physical memory is divided into little units called pages. That's the size on a x86, x64. So basically, all the memory is filled with zeros. As the OS and as processes start using memory, it's drawing from the zero-page list because that's where all the memory is at the start. By the way, it's easier to tell if you have too much memory than if you don't have enough. Because if the zero list never gets down to empty, what does that tell you? You should take some memory out and give it to a friend. So in a way, it's easier to tell if you have too much RAM than not enough. Now, that's not 100% true because we're going to see later that the zero list actually gets replenished when this list grows, and this list grows when processes die. But that's not something that happens often, processes dying or exiting, especially on servers. We'll come back to that in a minute. So as processes are coming to life, they're causing page faults, they're growing their working set, and the memory is coming from the zero list initially. So now on the left, let's say we've got a bunch of processes on the system. Each has a working set. If you wanted to see the working set size, do you remember which of these 2 columns is the working set? It's the mem usage, not the VM size. The mem usage is the working set size. That's the physical memory consumed by the process. And the other way to think about these 2 columns, the working set is the code and data that the process is using right now. The VM size is data only. Some subset of the VM size number is in the working set, maybe, and some of it may be in the paging file. That information is not shown. So you have no idea, looking at this column, how much of the private process memory is in RAM or in the paging file. It's simply not shown, and there's no performance counter to show that. So these 2 columns are apples and oranges. They're 2 very different animals. Mem usage is physical memory, code, and data. VM size is virtual memory, data only. So think about that. They're very different numbers. One could be larger than the other, or vice versa. So the process working sets exist. These processes are using memory. And remember, before the break, we said at some point when a process is paging and paging and paging, the memory manager will say, stop, you're big enough. Now, it doesn't stop the threads, but it stops the process working set from expanding. And again, what happens if a process wants to create a new page, but the memory manager has decided the working set is at the maximum? It takes a page away. That's what these arrows on the bottom are showing. This is what happens to the page when it's taken away. If the page was modified, it goes to the modified list. Now, what do I mean by modified? The program modified the data in memory. Go back to Notepad. I type some stuff. There is a page of memory right now that has that text in it. It's been modified. So were I to minimize Notepad and run other stuff for the next 5 days, what would happen to the working set of Notepad? Down, 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 down. So let's talk about where its working set would go. The private modified page that contained that text goes to the modified list. The unmodified parts of the process go to the standby list. So, code, pieces of the exe or DLLs. When the working set is trimmed, go right to the standby list. So the standby list basically represents cached file data. Another example, let's say I'm running PowerPoint, which I'm running right now. I open a PowerPoint file for slideshow. I don't modify it. As PowerPoint is running, it's causing page faults to read the PowerPoint file off the disk. Every time a page fault occurs, the memory manager has to get a page of memory to read in the piece of the PPT file, and that goes in the working set. So here's a piece of the PowerPoint file that's in the working set. Again, I haven't modified it. I'm just viewing the PowerPoint file. If I go on to 100 slides later, and I stop using that part of the PowerPoint file, the memory manager may trim that page from the working set. Where does that page go? Modified or standby list? Standby list. If I later go back to that slide, PowerPoint goes to touch that piece of its virtual memory address space and gets a page fault because it's not in the working set. However, it's still where? On the standby list. And so it comes flying back into the working set. That's called a soft page fault. So the standby list is effectively file cache. It's pieces of memory map files that once were in use that aren't used now. They're not in use now because they're on the standby list. If they were in use, they'd be in a working set. And they only get on the standby list if somebody had it in their working set in the first place. So it's file cache. It's file cache with a funny name. The modified list, however, although it's also file cache, is different than the standby list because this is data that has not been saved to disk yet. The standby list is a copy of data that's already on the disk. For example, the PowerPoint file that I read but didn't change. So it's the modified list that gets written to the paging file. That's what goes to the paging file. Anything that goes to the modified list. So again, in this Notepad process, the page in memory with that text is a modified page. Right now it's in the working set of Notepad. If I minimize Notepad and the working set gets trimmed and trimmed and trimmed and trimmed and trimmed and trimmed, the modified pages go to the modified list. The code unmodified pages go to the standby list. At some point, the modified list reaches a threshold, relatively small number, about 2 megabytes. And when it reaches that threshold, a system thread has his doorbell rung, called the modified page writer. That's a thread running a piece of the OS that is normally sleeping on an object called an event. And when there are modified pages to write, his doorbell gets rung. He wakes up and he begins writing those pages out to the paging file. Then he goes back to sleep. When those pages are written to the paging file, they're not erased from memory. That would be stupid because somebody might want that data again. The pages are moved to the standby list, where they can be faulted back into the working set without going to disk. So if you think about it, for a process to actually read something from the paging file, think about this. It has to create some private memory, stop using that memory so that the page gets taken out of the working set and put on the modified list. Continue to not touch that memory long enough for it to get written to the paging file and move to the standby list. And continue to not touch that memory long enough for the entire standby list to be cycled through, because it goes to the end, and then the system will overwrite that and use it for something else. Later, if the process calls upon that page, it has to read it from the paging file. So if you think about it, if you're seeing reads from the paging file a lot, that's an indicator that you need more memory. That's unusual. It's not unusual to see some out-paging occasionally, but to be constantly reading from the page file would be an indication that you need more memory. And unfortunately, the paging counters don't distinguish reads from the paging file from reads from PowerPoint files, XEs, DLLs, Word docs, etc., because they're just called page reads. There's no distinguishing between page reads from the paging file and page reads from data files. That's why I said if you look at the page read counter, you're clueless. Really, the only way is to get a file trace, and I'll talk about that in a moment, with something like FileMon, and look at what files are being faulted. If it's pagefile.sys, the paging file, okay, maybe you need more memory. If that's happening a lot, not occasionally. Okay, so we've covered the standby list and the modified list and the zero list. Let's talk about the free list. The free list, if you look at the arrow, grows at process death. When a process dies, the working set is disassembled. So for example, I'm going to exit Notepad, not saving the data. Where did the working set just go? Part of it went to the standby list. The reusable part goes to the standby list. So that would be the XE pages, the DLL pages. So that when I run Notepad again, This working set just got built by reading pages off the standby list. I didn't go to disk to read notepad.exe back in because it's already sitting in memory on the standby list. However, the data page, when I exit Notepad, that goes to the free list. That is a piece of memory that cannot be reused. It can't be given to anybody else. It's private, confidential, process private memory. Nobody can ever see that again. It's unreusable. It is not reusable. So that's what the free list is. It's unreusable pages that can't be recycled in terms of their content. Now, of course, the RAM is usable. And to make that RAM more usable, it gets zeroed out. That's done by another system thread called the zero page thread, who, like the modified page thread, is normally sleeping. And when the free list reaches a certain threshold, has his doorbell rung, and he goes in and zeroes out the memory. By the way, that thread runs at priority 0. The lowest priority you can achieve in a Windows program is 1. So that will never run if there's real work to do. If there's no user thread that wants to run, and this guy wants to run, he'll run. And when he's done, do you remember where the system goes when there's nobody who wants to run? The idle thread. So it's a very low priority operation. And in fact, if the system is so busy that this guy can never run, no problem. Because if the system needs a zero-filled page, it will take it from here and zero it at that point. It's just if there's nothing to do, it does that in the background. So let's hope that your zero list has been emptied. Let's hope you've actually used all the memory in your system. Likely you have. So this is normally empty. This only grows when the free list grows. The free list only grows when processes exit. How often do processes exit on a server? Not very often, if at all. Even on a workstation. I mean, most people, they start Internet Explorer, they start Outlook and Solitaire. And then they use Solitaire the rest of the day. Seriously, on a workstation, how often do you exit a process? Not constantly. So if the free list grows at process death, and that isn't happening often, this list may be small or empty. So if there's no memory here and there's no memory here, where is the free memory when the system needs free memory to create a new process? The standby list. The standby list is 2 faced memory. Let me do that again. 2 faced memory. Want to do it? It's 2 faced memory because it's free memory and it's file cache at the same time. It's free memory because nobody's using it. It's immediately usable. It can be overwritten right now without hurting anybody because it's a copy of something that's on the disk already. So in that sense, it's free. It's file cache because it's a copy of something on the disk. That's the definition of file cache. So now we can put a nice definition on available memory. Available memory in Task Manager is the sum of all 3 of the lists on the right. The free list, the standby list, and the zero list. That's what the system considers to be the available memory. That's what that performance counter means. It's the sum of those 3 lists. But that number by itself, when you bring up Task Manager and look at it, so my system has 330 megs of available memory. I don't know whether that's 330 megabytes of file cache, that would make me feel good, or 330 megs of zeroed memory that I've never used and should take out and give to a friend. Right? You have no idea what the breakdown is. And that's why on the next slide there's a pointer to a kernel debugger command, the mem usage command. This is a kernel debugger command that can show the breakdown of the list. Now, I haven't introduced the kernel debugger. I'm going to mention it now. That's a use of the WinDBG tool, which you saw me run earlier, to, instead of connecting to a process, connects to the OS. And as of XP and later, you can do this on the live system. Prior to XP, it required 2 computers to look at a live system, and the target had to be booted in debugging mode. So file kernel debug, local tab, as opposed to specifying a COM port that's connected to a target machine that you're going to debug. So the local tab says kernel debugging of the local machine. That's XP and later. Click OK, and it's now connected to the local system, and I'm in the kernel debugger, and now can use one of the 75 different commands that let you explore the kernel state. And that goes way beyond what we've seen with Process Explorer. Many of the experiments in the book that, if you've looked at it, even the previous edition, are kernel debugger experiments, because the kernel debugger lets you explore kernel state, and it obviously provides access to a lot of details that simply aren't available from any user application. And by the way, for those of you that came in late, they're running a special. I didn't know about this till this morning. They're selling the book upstairs. All right, so let's try this bang mem usage. So bang mem usage queries the database that the memory manager keeps and shows the breakdown. So let's look at my system right now. So should I take 7 megabytes out and give it to somebody here? The zero list has 7.7 megabytes. That's in kilobytes. The first column, by the way, is a number of pages, so ignore the first column. Look on the right. Should I take 7 megabytes out? Likely that's zeroed memory that got there because I exited a process which dumped its private pages to the free list and got zeroed. So I'm fairly confident that I've actually used all the memory in my laptop since I booted. The zero list did go down to empty at some point. I have a little bit on the free list that when I did this snapshot hadn't been zeroed. It's probably zeroed by now. So that 872K has moved up. And there's the answer. Of that 330 megabytes, 300,000 kilobytes is file cache. So now I feel good about my available memory because, in fact, it's serving me. It contains useful stuff as opposed to its memory I've never used. And that's typical what you're going to find. A third to two-thirds or a third to a half of the RAM is on the standby list. And the rest of the memory is in use. 700 megabytes, process working sets, and OS memory, drivers in the OS code itself. That's the only way to get the breakdown of the list. There is no other way except the kernel debugger, if you cared. So if that's the sum of the zero, free, and standby, what's the system cache number? The system cache number, and this is not on the slide, is the size of the standby list plus OS code and data that represents file cache. So system cache is actually the right number to look at for how much of your RAM contains cached file data. It's the standby list plus some other stuff that represents file cache. That is data that the OS has read off the disk that's not on the standby list. And if you could tell, if I look at my system just by this alone, the fact that my system cache is 425 megs and available is 313 megs sort of suggests that available memory is almost all standby. But the standby list is counted in both numbers. You can't add them together. Standby is included in available, and standby is included in system cache because it is, I won't hit myself again, two-faced. It's available and it's system cache. That's why it's included in both. Now, given this, how can we tell if we need more memory? We just described, I hope now it's clear, that page fault activity doesn't necessarily show it, because some hard paging is unavoidable when referencing a data file you've never referenced before, at process startup of an exe you've never run before. So here's the Solomon-Rusinovich simple formula. If available memory is a small number most of the time, more memory would probably help you because you'd have more file cache. How small is small? You'll know it when you see it. 10 megabytes, 20 megabytes, I don't know. Depends on how much RAM. I don't have an exact number. But if that number is staying small all the time, your system is not keeping any file cache. Other than that, you've got to go do an I/O trace. The only other way is to really look at what files are being read. For example, if you are constantly reading from the same part of the same files all the time, then you don't have enough memory to keep that cached. That's broken if you keep reading the same part of the same file. Or if you keep reading from the page file constantly from the same part, more memory might be indicated. Again, the same part is important because if you are reading from a different part of the page file every second, you never go back to reread the same part. That means that you created some huge number of processes, stopped using them, and then went back to use them all again. But if you don't go back to the same place, it's not clear that more memory is going to help. make that faster the next time around. So how do you get a file trace? FileMon from sysinternals. And the only caveat I want to mention about FileMon is it does not show reads from the paging file unless you have advanced output selected. It does not show reads from the paging file. It shows page reads from any file or every file but the paging file. Now that you have an exact understanding of what goes to the page file and when, and again, just if you forget, remind yourself of this picture. What goes to the page file? Modified pages that hang around here long enough to get written to disk. By the way, if a modified page is taken away from a process and then referenced right away, it comes back in the working set without being written to the paging file. So it has to be modified data that you stop using that stays on the modified list long enough to be written to the paging file. So given that's what goes to the paging file, how big should your page file be? Is it a function of RAM? The more RAM you have, the smaller page file you need. So any formula that sizes page file as a multiplier of RAM is ridiculous. Now, the only case where you might want to have your page file be related to RAM is if you want to take a full crash dump. I don't recommend full dumps. Since Windows 2000, there's a nice middle option between mini dumps and full dumps. Anybody know what it's called? Kernel dumps. That dumps kernel memory, which is a small subset of physical memory. But if you wanted to take a full memory dump, because the memory dump, as we're going to see later, is written to the paging file, your paging file would have to be at least the size of RAM. But full dumps are not necessary. Do you even need a paging file? That's a myth. NT has never needed a paging file. In fact, if you go to the page file dialog, as of XP, it is in your face that you don't need a paging file. Look at the new radio button in the paging file sizing selection. Do you see that? No paging file. That wasn't there in Windows 2000. You could set the page file size to 0, but it wasn't a radio button. So you don't need a page file. You've never needed a page file. The page file is there so that the system can dump modified pages when the modified list gets too big. If you don't have a page file, the modified list doesn't get written out to disk and it just grows until you run out of memory, and then you can't create new processes anymore. So the modified list has no place to empty, it just stays in memory. So if you were going to size what goes in the paging file, it's really dependent on what could be paged out, and what could be paged out is the private memory space of each process. That is a number that we looked at in Task Manager. What's the column that I said was the potential page file usage? VM size. So if you totaled up the VM size column, that would be the amount of page file space that you would use at this instant if every one of those processes were not deleted, but evicted from RAM, which never happens. They might get shrunk, but they're never going to be completely evicted all at once. And you don't have to do the arithmetic. It's done for you because it is the commit charge peak. So let's map this to something that we saw in Task Manager. Remember the commit charge section down here? Now we're going to put some labels there. The commit charge total, by the way, that's a typo. That should be a number 2. The commit charge total is the potential page file usage at this instant. The commit charge peak is how big that number got since you booted. So if you were going to size your page file, I'd take the peak, not the total. The total is the current potential page file usage. The peak is how big that got since you booted. So if you look at the peak after you've had your system up for a day or 2 or 3, that is the size page file that you would have needed in the worst possible case, which will never occur. That number is completely disconnected from the RAM on your machine. And just to illustrate that, if I brought up Task Manager and looked at my commit charge total right now, here's my commit charge total. If I shut my computer down, doubled the RAM to 2 gigabytes, rebooted, logged in, and ran the exact same set of apps with the exact same clicks and the exact same keystrokes that got me to this point in time, that number would be exactly what you see there. If I shut the system down and took the RAM down to half a gigabyte, I had a gig. If I put it to 2 gigs, I'd come up with that number. If I brought it down to a half a gig or 256 megabytes and rebooted and went through the same set of clicks, my commit charge total would be the exact number that you see there because it's completely disconnected from RAM. It's a function of the virtual memory in use by the processes that you happen to be running now. That's a function of the app, not the RAM on the machine. So I hope that makes it clear. Increase or decrease RAM, that number doesn't change at all. If you look closely, this number is another place on the same display in a different unit. Anybody see the commit charge total? Another time on the same display in a different unit. That's what this is. The PF usage is not the page file usage. It's the PPF, potential page file usage. It's shown in gigabytes, so unless you're a computer science geek, you might not realize that this number of kilobytes is that number of gigabytes. Do the math. It's exactly the same number, but expressed in either megabytes or gigabytes. Same exact performance counter shown in 2 different units, which is confusing. So the page file usage is the PPF. And to emphasize that, if I rebooted with no paging file, your PF usage would be the same exact number because it's the private virtual memory in the system, whether you have a page file or not. So PF usage is not a terribly clear title for that. It's the total system commit charge at this point in time. It's the potential page file usage. So that's hopefully a clear explanation of the commit charge total and the peak. The limit we talked about earlier is the sum of your paging files and the amount of RAM available to you. Remember I said of my 1 gig laptop, about 900 megs were available. And that's why my commit charge limit with a 1,000 megabyte page file was about 1.9 gigs is what it was on my system. So now you know how to size your paging file. Just to see if you got at the point, if your page file is too small, will your system run more slowly, yes or no? Let's take a vote. If your page file is too small, will the system run more slowly? Who says yes? Who says no? The majority's correct. It's no. It has nothing to do with system performance. If it's too small, your system doesn't run slower. It just means you can have less stuff open at the same time. That's all. It's a little difference there. Who was that? You know what? We're going to sign out right now. That's a friend of mine from Beirut. I actually have a funny story. I was at a TechNet in the U.S., and my mom sent an instant message that appeared in front of 750 people while I wasn't paying attention. And it was some, like, did you bring enough underwear kind of question on your trip. And since then, I did have MSN Messenger signed out. I think I signed in a demo earlier. Whew, that was dangerous. Okay. So the size of the page file doesn't affect system performance. It affects how much stuff you can be running. If your page file is too big, does that affect system performance at all? No. Doesn't slow it down. It means you can run more stuff. Now, if you have no paging file versus a paging file at all, does that affect system performance? A little bit, because if you have a paging file, the system will send stuff there, but it only sends stuff that isn't being used anymore, which is a good thing because then the system can use that memory for something more useful. So I would say it's better to have a little paging file than to have no paging file, and that's not really intuitive. Think about it. If you have one, the system can use more memory for useful stuff rather than not being able to save stuff to disk. Okay, last topic is memory leaks. And we're going to look at memory leaks both at the process level and at the system level. Who's seen the message box system running low on virtual memory? If you read the text, it says, please increase the size of your paging file. If there is something with a memory leak and you follow those instructions and reboot, what will happen the next time? You'll get the same message later. And you'll follow the instructions and you'll get the same message later. And you'll keep getting the same message. So I suggest instead of increasing the size of your paging file, look for a memory leak. And by the way, even if you didn't have a memory leak, the message box should say, system running low on virtual memory. Check if there's a memory leak. If not, and you can afford it, buy more RAM. If you can't afford it, increase the size of your paging file. If your system commit limit is too small, the system commit limit is the sum of RAM plus page file space. Increase either one, and the commit limit goes up. If you have a choice, it's better to increase RAM. It doesn't suggest that either. Okay. It's so trivial to find out if there's a process with a memory leak. Sort by the VM size column, or look at the private bytes counter. It's the same number if you're using perfmon or Process Explorer. Bring up Task Manager, sort by VM size, you're done. So 270 megabytes of private virtual memory in the Avant browser process. Now I have like 45 web pages open, so that's not a bug. The other thing is it's not going up, is it? So that's not leaking. That's a pretty hefty process. And the fact that the working set size is 56 megs, look at the mem usage number, it's 56 megs, tells me that of the 270 megabytes, a small part of that is in the working set. Now, does that mean that like 200 megabytes of its private virtual memory is in the page file? I don't even know that. That could all be on the modified or standby list. So even that I can't tell. All I know is that 56 megabytes is what's in the working set. It has 270 megabytes of data that's not in the working set. I don't know if that data is in the paging file and or on the standby list or on the modified list. It's simply not shown. If you'd like to generate a memory leak just to see what happens on your system, you can run Outlook. Or, here's a tool in the resource kit that will do it more quickly. That was a joke. I love Outlook, for anybody from Microsoft that's watching. Leaky App is a tool in the resource kit that continuously allocates memory. So it's just basically creating private memory, and it does that until there is no more. And instead of reporting an error, it just continues to allocate memory. So if you exit something, it will soak up the free memory that's been freed. It just constantly is grabbing private virtual memory. So if you'd like to see that message box and kind of see what happens to your system when your system commit limit is reached, then you can run Leaky App. Now, on most systems today, our RAM size and page files are so big that if you ran this once, you're going to have time to go out and do shopping and come back, and your system is still leaking, because it leaks slowly. So if you'd like to get it to happen more quickly, run 10 copies. Have 10 processes that are leaking at the same time, and then you'll see the memory usage going up. So that was process memory leaks. Now let's talk about something that is in a way more serious, although a process memory leak that causes the system commit limit to be blown, in effect, causes that box to become unusable because you can't create other processes. Kernel memory leaks also may cause the box to become unusable. Now, when I say unusable, I mean you can't create new stuff and apps may start failing. Not a blue screen. The system shouldn't crash. Processes might start to crash if they are not handling the out-of-memory condition gracefully. So how would you determine that you had a system memory leak? If one of the two kernel memory numbers that show up in the lower right-hand half of Task Manager's Performance tab, that's the kernel memory paged and non-paged. So let's talk about these two memory pools. There are two kernel memory pools, non-paged and paged. And the name is fairly self-explanatory. Non-paged pool can't be paged out, and paged pool can be paged out. Now, why are there two? There's a technical reason that device drivers, when servicing interrupts, are in a state where the system cannot do in-paging. Let me repeat. Device drivers, when servicing interrupts, cannot touch memory that could be paged out because the synchronization mechanisms in the kernel don't permit waiting at interrupt level. And when you do a page fault, you have to do a disk read and wait for the read. So the OS provides two memory pools. One is non-pageable and one is pageable. So drivers that need to touch data that describes the I/O request that they're processing that kind of data has to be allocated from non-page pool if it's going to ever view that data from interrupt level. Otherwise, drivers are told to allocate from page pool because that's the better choice if there's a choice. Because if you allocate from page pool and the driver doesn't use the memory for a while, what can the OS do with that? Write it to the paging file and then use that memory for something else. Non-page pool can't be paged out. Now, what's not shown in Task Manager is how big the pools could be. That's the current size of paged and non-page pool and the total of the two together, but not the maximum. The maximum sizes are computed at boot time, and it's a function of how much RAM you have and whether you're a server or a workstation and a few other factors. So the OS basically decides that for this machine, a non-page pool maximum of this is good for you, and a page pool maximum of this is good for you. Well, that may not be good for you, in that you might be running enough strange stuff, strange drivers, that need more kernel memory than the system configures. Well, you can specify it. You can change it. You can pick your own numbers. There's a registry key that underneath has values for the non-paged and page pool size. It's unusual, but there are cases where you might need to up the default calculation. However, you can't make the number arbitrarily big because non-page and page pool have to fit within the kernel memory area, which on 32-bit Windows is how big, virtually? 2, kernel memory, 2. Maybe 1 if you booted 3 GB. So there are some limits, and the limits are on the next slide. 32-bit Windows, 256 megs for non-page pool. 650 megs for page pool. On 64-bit Windows, the numbers are quite a bit bigger, 128 gigs for each. And again, those are version 1 numbers that could get bigger easily later. There's a lot of breathing room. In the 32-bit case, there isn't any breathing room because in this 2 gigabytes of virtual memory for the OS has to fit itself, all the drivers, and then this data. And there's other stuff also that takes up kernel memory. So those are limits that are just about reaching their end. There is some work in the next version of Windows, codename Longhorn, or some people call it Shorthorn, that is going to increase these numbers some more, but still, ultimately, what's the limit of those numbers on 32-bit Windows? 2 gigabytes. And not 2 gigabytes each, because they have to add up to 2 gigabytes, and there has to be space for the OS code, driver code. So they are going to get bigger, but still, they're reaching the limit of the 2 gigabytes of total kernel memory. So 64-bit Windows is a big step up in terms of kernel memory resources. But that's the upper limit. When you boot your system, it picks a number that's probably smaller than these maximums. So how do you tell what the maximum is? There's another kernel debugger command, bang VM. So let's go do that. Back to the kernel debugger. Bang VM. And this shows a bunch of memory-related statistics on the system. One of them being, there we are, non-paged pool usage and maximum, page pool usage and maximum. So Task Manager shows you the usage. It doesn't show you the maximum. But if you look at those numbers, am I okay? I'm good, right? I got plenty of room. But those maximum numbers, to me, are pretty important for you to at least once observe on a server box that you're managing. Because if kernel memory is exhausted, it's too late to do any troubleshooting. You can't run any tool to troubleshoot why the system ran out of kernel memory. Your basic only option at that point is to do what? Reboot the box. So I think you should be setting an alarm on the kernel memory numbers. There is no performance counter for the max. You've got to find the max. But you should set an alarm on the current usage so that if it goes above some normal threshold, that you get some notification before you reach the end, because at that point it's too late to diagnose why you ran out. So either run WinDBG, configure the kernel debugger. It also needs the symbols. I mentioned the symbols earlier. You have to point it to the symbol server. It needs the symbols for the OS image. So just like you saw in Process Explorer, I had symbols configured. Likewise, I've got the same exact string in the symbol path in the debugger. And that's all described in the documentation pretty clearly. The other is, Mark, because this is such an important number, shows the limits in Process Explorer's System Information Dialog, which we haven't brought up yet. That's sort of his clone of the Performance Monitor, Task Manager's Performance tab. So I'm going to go bring that up now. View System Information. So that should look similar. If I bring up Task Manager and put them side by side, can you see in the kernel memory section? Oh, there's a painting bug. There we go. If you see in the kernel memory section in Task Manager, it's the total and the current size. Process Explorer is showing the limits, not just the current size. So that's another way to get the limits. In order for it to do that, it's got to have kernel symbols. It's got to be able to get access to the same information the debugger needs to go dissect where data is in the kernel. And if you don't have symbols configured properly, you'll see no symbols. Right there, it won't be able to show you. Okay, so that's another way to get the kernel memory usage and limits. Now, the interesting question is, what do you do if non-paged or paged pool is climbing slowly, other than reboot the box? Well, Mark wrote a program that lets you simulate a real kernel memory leak. It's not a simulation. It is a real kernel memory leak. And it's a feature of an app that's on sysinternals, but it is not mentioned or linked from any page. This is a zip file that, if you type into your browser, will download a program called notmyfault.exe. And the reason Mark calls it notmyfault.exe is that when you run it, it loads a device driver called myfault.sys. That just loaded the driver. The driver, again, is buried in the exe. He extracts it, loads it, deletes it. So I'm now, on my system, I've loaded the driver, and this driver can do one of 8 very bad things in kernel mode. So you've got 7 radio buttons and a do bug button. And I'll talk about that in the crash section, because we'll use that as a way to generate blue screens. Do bug does the bug you've selected. And those things either cause system hangs or blue screens. In fact, those generate the 7 most common kernel mode kind of issues that Microsoft Product Support sees. We talked to them and we found out what are the most common crashes. This is a program that generates those kinds of crashes. But I'm not going to press do bug, because I don't want to crash my system. I'm going to use the leak pool. Leak pool leaks pool. And by the way, when you exit, it doesn't release the pool until you reboot. So I'm going to start leaking. We have a real live memory leak going on. Can you tell, looking at the kernel memory numbers, which pool his driver is allocating from paged or non-paged? Paged. Now, if I didn't stop this, what would happen to my system ultimately? My page pool would reach the maximum, which was about, was it 200 megabytes? I don't remember from the debugger. We could go back and look. I had it right here. It's my page pool maximum, 163 megabytes. So I'm up to 81 megabytes. So if I let this run and run and run, I'd basically be in the state where I'd have to probably power off. I probably wouldn't even have enough pool to do a normal shutdown. Since I don't want to do that, I'm going to stop leaking while I continue to explain. Now, by the way, when I exit, it doesn't free the pool. It's a permanent leak until you reboot. Not a big deal, since I've got plenty of extra breathing room there. So how do we diagnose this? There's 2 basic approaches. One is using a very old tool. It's part of Windows XP support tools. It's been around for a long time, called Poolmon. It's currently in the support tools. And the other is to use a feature of driver verifier. Let's talk about Poolmon first. Poolmon requires that you turn on another one of those flags that you saw me reference when I talked about looking at the open handle table. Remember I ran G-flags, G-F-L-A-G-S, it was part of the support tools, and I said I had 2 options on. It's the first option that you need on to use Poolmon. That option is on by default as of Windows Server 2003 and later. Permanently on, you can't turn it off. But for XP in 2000 and NT4, you've got to manually configure it. There is no serious resource issue turning it on. Again, Microsoft has now decided that it should have been on. It's on all Server 2003 systems and later. So safe to turn on. And in fact, I recommend you turn it on, because when you need it, it's too late to turn it on because it requires a reboot. So given that that pool tagging option is on, you can run poolmon from the support tools. When poolmon starts up, it shows the usage of non-paged and paged pool divided into categories that show the summary of the memory utilized by each tag. If you look at the first column, it says tag. The tag is a 4-byte code that the driver passes to the OS when it allocates memory. So it's the driver, when it allocates memory, that says, please give me a piece of memory and call it Fred. So the line that says Fred would show how much memory is being used by all the memory identified as blobs called Fred. So it's the driver writer that picks this number, this name. And Microsoft doesn't have any formal registry of pool tags, so sometimes driver writers use names that have been used in other drivers. Now, some of them are obvious. For example, if you look at the 1394 line, those pool tags are probably from what driver? FireWire driver. And if you've noticed, there's two lines. The FireWire driver evidently allocates some paged memory and some non-paged memory, which is fine. So you may see the same pool tag twice. Now, going across the columns here, number of times that tag was allocated, number of times that tag was freed, and the difference. So the difference would indicate blobs of memory, how many blobs in that category have been left in the system. The number of, what happened to poolmon? I exited it, sorry. The next column, number of bytes, is the total amount of memory in use by that pool tag. So which of these do you think would be the right number to look at in terms of looking for a kernel memory leak? Which column? Diff maybe, or bytes. Now the reason I say diff may not show is that the memory that's using kernel memory could be a small number of really big chunks. So diff might show you have 43, 44, 45, 46. But if the pieces of memory that are being allocated are small, then that's not going to show up as the highest number if you sort by that column. Bytes, however, is going to show how much real memory is in use by that pool tag. So I'm going to press B for bytes, and I'm now sorted by the bytes column. And the first column says G805. I have 22 megabytes of G805 structures. What the heck is a G805? Well, how do we find out what these pool tags mean? When you install the Windows debugging tools, it includes a file in a subfolder called triage, which lists the Microsoft registered pool tags. So shall we go look in there for G805? Let's take a look. So I'm going to bring up a command prompt, go to my Program Files Debugging Tools, go to the triage subfolder, and open pooltag.txt. And again, this is a Microsoft supplied file that lists in alphabetical order the pool tags used by the Microsoft components, the OS and the drivers. Now the G section, there it is, GDI objects. Things having to do with graphics, windowing related data structures. So I have 22 megs of GDI object data in my page pool. That doesn't necessarily look bad. It's not growing madly. This is a desktop, and I have lots of open windows, so the fact that I have 22 megs of GDI objects doesn't sound bad to me. Now, if that thing was going up, then I'd wonder if there's a bug in the windowing system. Let's go back and continue the leak. I'm pressing leak pool again. So now the pool leak is in progress. Poolmon highlights pool tags that are changing. Anybody see a pool tag whose total bytes is going up? It's the fourth line, 663, 714. See it? The leak tag. So that's suspicious, right? Here's a pool tag whose total memory usage is going up and up and up. In fact, shortly it's going to climb. It's now in the number 3 position and growing. So let's stop the leaking. Now, if I look for the pool tag leak in this text file, what do you think? Not found. And that's going to be true of any third-party driver pool tag. It's not in the Microsoft registry. So how do you find the third-party pool tags? Strings from sysinternals. Dump the strings of every driver in the system. The pool tag text is going to be buried in there somehow. So I'm going to use strings to dump the strings of every driver, and I'm going to pipe it to the Windows NT equivalent of grep, which is spelled FINDSTR. So I'm executing the command right here on slide 42. Strings, Windows, System32, drivers, star.sys, pipe it to grep, search for leak. That's how you spell grep on NT, right? FINDSTR. Done. myfault.sys. So inside myfault.sys, which is Mark's faulty driver, is the text leak. We found the pool tag. We're done. If you have the device driver kit from Server 2003, the poolmon tool has a switch which will do what I just did for you and generate a pool tag text file that has all the pool tags from all the drivers on your system. Either way. But, you know, I just made a big assumption here, folks. What assumption did I make with that command? That all the drivers are in that folder. And that the files even exist at all. Thank you. Do drivers have to be in that folder? No. You can install them anywhere. In fact, antivirus products typically, their drivers are in their program files folder. So that's why this next slide is there just as a reference. While most drivers are in the drivers folder, they could be loaded from anywhere. So a couple of ways to look at the full driver list. MSInfo32 has an entry on the tree structure it shows of system information that shows the drivers on the system, and it shows the full path. So you could sort by that. There's a new XP command line command, driver query /v. That shows the full path of every driver. That one I'll demo. Driver query /v. So you see the name of the driver and the full path. But that's not going to get drivers that are deleted after they're loaded. Deleted from the registry, that is. And that's something that Mark's tools do routinely. So there is a way to list the drivers loaded on the system that have been deleted from the registry and potentially deleted from the hard drive. And here's 3 ways to do it. The drivers tool in the resource kit, that's an old tool, shows the list of loaded drivers. And look, there's Mark's Process Explorer driver. There's his FileMon driver. There's his RegMon driver, and so forth. So that's querying a different list. This is not querying the registry. This is querying something called the System Loaded Kernel Mode Module list. And when a driver is loaded, it's in that list, even if it's deleted from the hard drive and deleted from the registry. Now, there are some drivers that are in the category of advanced viruses called rootkits that hide themselves from that list. And then you're stuck. We're not talking about rootkits. If you'd like to be really depressed, go to rootkit.com. Anybody ever been to rootkit.com? It's depressing, isn't it? Scary. If you would like to be frightened beyond your wildest dreams about the security of your entire computing infrastructure running Windows, or really any OS, go to rootkit.com. See what people are doing with self-hiding viruses. Mark's actually putting quite a bit of work into providing tools to try to expose those kinds of things. And just recently, since I mentioned it, I'll just give you a pointer on sysinternals. He's released a free rootkit revealer that does some low-level scans to try to list these kind of advanced viruses and malware that are trying to hide themselves from the system. In fact, he just released an update earlier this week because already, when he released the first version, one of the most popular rootkits is a general term for these advanced viruses that hide themselves from the system, and it was fooling Mark's tool by, when Mark's tool was looking, it would tell Mark's tool that I'm here, which means that when he looked at the low level, it was there, the system was reporting it at the low level and reporting it at the high level. The rootkits hide themselves often by, at the system call layer, intercepting those, and when you look at the process list or the list of files on your disk, they don't return themselves. So Mark's tool basically is asking both. asking the system what files are there, what registry keys. And then it does it at a very low level. And if something shows up at the low level but doesn't show up at the normal way, that's a rootkit trying to hide itself. So the rootkit people went in and said, okay, well, we'll fool his program by revealing ourselves to his program so he doesn't think that something's being hidden. I'm not kidding. This happened within days of him releasing this tool. So his most recent version generates a random executable name every time you run it, so that the rootkits can't easily tell. Now, they still could tell because they could do what? Look at some CRC, check the... They could, if they wanted, check the executable making the call and still determine its program. So this is just yet another step. It's an ongoing battle. Anyway, drivers.exe, the lm command in the kernel debugger, those are ways to look at that system loaded module list. Okay, we're almost done with the memory manager. Pool leaks. Poolmon was one technique. Driver verifier is the other way to look at pool usage. Driver verifier can track pool usage for individual device drivers. And using driver verifier, it's easier and in a way harder. It's easier because if you use driver verifier, it's going to tell you driver A is using this much memory, instead of you having to take the pool tag and mapping it back to the driver. However, it requires that you reboot. You have to configure which drivers you want to track. And when you reboot, you then have to check the pool usage of each driver periodically. And when you see a driver whose memory usage is going up and up and up and not down, you found a leaker. So it's easier and it's harder. It's easier because it's the name of the driver and the memory usage, and not the pool tag nonsense. But it's also less convenient because you've got to configure it ahead of time. Whereas the pool tracking, which I recommend you turn on all your computers, is always accessible to Poolmon. That's it for memory troubleshooting.